a little bit then today. Okay, so yeah, Gage, if that ever happens again, just come. Right, we'll take care of that, right? I'll take care of it. All right. Okay, so here we go, guys. We're on example 4. I think you've done a really nice job with this stuff right here. So I am kind of concerned about this example right here, so I want to make sure we're okay with this. Example 4, a couple of things that we have to do. We have to learn how to write some exponential functions, okay? Now, this one here, it says to rewrite each function to determine whether it represents growth or decay. All right, and then identify the percent rate of change. Here's what I'm going to tell you right now. When I talk about this idea of identifying the percent rate of change, everything is based I'm going to write it in here like this. Everything is based off 100%. So guys, if I say this, I gave 107% today. What's my percent of change from yesterday? Well, if everything's based off of 100%, how much more than 100% is 107%? So your percent of change would be 7%. What if I gave 92% today? What's my percent of change? Okay, and you don't even need to say -8. You just say it's an 8% decrease or something like that. Okay. What if I say I gave 125%? What's my percent of change? Okay, does that make sense to you? So when I talk about percent of change, base it off of how far off of 100 are you. Okay. So here we go with this right here, kids. We need to know what's going on here. Now, kids, this is a little different right here because we're used to seeing exponential functions where this is written such that you have a base b 1.02 right here, but it's just usually to the t power out here, okay? We want to be able to write a function of the form y equals a times b to just the x out here. And if you notice having just a t out here, what do we have out here as an exponent, kids? 10t, okay? Now, I'm going to go to a different page. You don't need to write this down, but kids, do you agree that x to the second all to the third like this from our rules of exponents would equal x to the what, kids? So when I had that, what was it, 1.02 to the 10t, shouldn't that be written like this right here? Because wouldn't I bring the t into the 10 to call it 1.02 to the 10t like this? So here's a question for you. Couldn't I evaluate 1.02 to the 10th power? See what that number is? Could I do that? Okay. So here's what's happening in this right here. We're trying to write, whoops. Oh, where's the page at? We are trying to write this so that it only has one exponent. And the way you would do this one right here, we write this as 3 times 1.02 to the 10th power all to the t power like that. Okay. So now what we can choose to do here, kids, we can call this part right here, this part right in here. We can evaluate that. So who has a calculator handy for me this morning? I need you to punch in 1.02 to the 10th power. Take 1.02 and raise it to the 10th power for me. What do you get when you punch that in? 1.02 to the 10th. Let's go 2 places on the decimal.
1.21.
1.21? How many are agreeing 1.21? Okay, is this
1.22 actually.
Say again?
It's 1 point.
1.22 if you're round?
Yeah.
Is that what you got right there when you punch that up? Okay, how many agree 1.22? All right. So this part that I evaluated right here, kids, this really makes this problem equal to my start value of 3 times 1.22. That came from all this right here, didn't it, kids? To what power now? 8. And now I have just that exponent out there. Nothing else. Okay, nothing else. All right? Guys, what's the growth factor in that right here? What's my growth factor? We start with 3 and we have a growth factor of 1.22. Now guys, if I was going to turn 1.22 into a percent, what percent would 1.22 be?
22%.
Okay, that'd be 122%, so the percent of change is going to be 22%, right? You're looking at that as a right. So here's the deal. It says 2 things that we had to do. We had to rewrite this function to determine whether it represents growth or what? Well, guys, is this value in here, is this growth factor or a decay factor here? That's a growth factor because it's more than what? So we know we have growth. We know we have growth. Kids, I'm going to make a note down here. 1.22 growth factor is like 122%. So how far away from 100% is 122%? It's 22%. We have a growth of 22% in this situation. Okay. Let's try another one. Okay. You all understand here how I did this. This 1.02 to the 10th to the 10t power is like 1.02 to the 10th, because what happened with the 10 and the t? Well, they got multiplied to make that 10t up there. You guys remember that from your rules of exponents? Okay. All right, so let's try another one. This is a little different. This is kind of, what do you notice about the exponent? Is t alone out here, kids? No, it's not. Okay, so we have to be careful on this, all right? I've got to kind of go back to a rule like this, where this x to the t plus 2 power up here on the board, that's the same as x to the t times what? So would you guys agree, based on what we saw up there to start class today, we would say y is equal to 0.95. You want to help me with this one, Logan? 0.95 to the what first?
T.
T? Thank you. Okay. Times 0.95 to the what, kids?
Second.
Okay, now is there part of that you could evaluate at that point?
Yeah.
Can I evaluate 0.95 to the t? But could I evaluate 0.95 to the second power, kids? Okay, so somebody see what 0.95 to the second power is in their calculator.
0.902.
So I'm going to call it 0.90. So this is really equal to 0.90 times 0.95 to the t power, isn't it? You guys agree with that? I know I'm going quickly. This is kind of a tough concept, so are you on board with me right now? Okay. Well, which value has the exponent, the 0.90 or the 0.95? 0.95 is a percent, is like what percent? So is this an increase from 100% or a decrease from 100%? This is going to show decay by what percent, kids? Yeah, it's 5% off of 100. So this is going to be a decay problem by what percent? 5%. You guys got this. This is cool. Okay, my main question is this. Do you understand how the 1.02 turned into 1.22 here? Okay, that became 1.02 to what power here by rule? 10th. I can do 1.02 to the 10th. That's the 1.02 to the 10th, and then the t stays outside like this when they're multiplied. Okay? Well, like the t plus 2 right here, if I'm adding exponents like this, isn't this really 0.95 to the t times 0.95 to the 2? Wouldn't I have to add these exponents to write this up here up top? Where'd the 0.90 come from? 0.95 to the second, and said, okay, this is really 0.90. This part is 0.90 right here times 0.95 to the t. This is my growth or decay factor right here because the exponent is here. You would say, oh, that's like 95%, which is how far below 100%, kids? 5% below, okay? All right. Questions? Gracie? No? All good? Okay. Last example. Let's try this right here. Okay. Hey, I want to go back to the beginning of the notes. And you don't have to do this. Just hang out with me. Does this car price increase or decrease, guys? Anybody 16 in here yet? Gage is 16. You're going to go out and buy a brand new car, right? Gage buys that brand new car to drive to school, right? And the second Gage drives that brand new car off the parking lot or off the sales lot. What happens to that? Decreases in what? Value. Okay? Over time, it gets used, it's going to decrease in value, right? Do you know anything that increases in value? if you buy something that increases in value over time?
Land.
Baseball card.
Baseball card, maybe?
A
Land.
house.
A house? What did you say on?
Land.
Land? Yep. Although the market for land right now is kind of, I think it's down a little bit right now, isn't it? From where it has been in the past. But typically over time, those things appreciate. But car values, they do what? By the way, do you guys know what the best car is that holds their value? What brand holds their value the most?
Toyota.
Well, you can see either Toyota or Honda. Okay? Yeah, guys, I'd tell you right now this. You want some real life advice? Did I give you real life advice yesterday?
No.
Two things that you can do in life. As soon as you can, start affording it. Buy a house if you can, okay? Don't rent. Buy a house if you can, okay? Because when you rent, it's okay to rent. You just, when you're renting something though, is it really truly yours? No. Okay, buy something because if you turn around and sell it, it's going to appreciate over time, earn more value to it, and get more money back on that. Second thing is buy life insurance as early as you can, okay? Buy a life insurance policy as soon as possible, okay? All right, right here. This is going to be an exponential decay right here. You guys see this formula right here? We talked about it. If we ever talk about percentage rates, you want to use this A times 1 minus R or 1 plus R formula right here. So we're going to come back to this. We're going to have an exponential decay problem with this car. So an example 5. Let's say the car that we're going to purchase is how much, kids? $15,000. And then each year it's going to lose how much money?
10%.
10% of its value every year. Okay, so the first thing that we have to do is write a function that represents the value y in dollars of the car. Thing I want to point out is this. If you ever see a problem that involves percent, you'll either use y equals your starting value a times 1 plus r to the t power, or you're going to use y equals a times 1 minus r to the t power. Okay? Now this is a decay problem because the value of the car over time is going to do what? Go down. So am I adding 10% value or subtracting 10% value each year? So which of these first two equations do I use? The first one or second one? We're going to use the second formula right here. Okay? So we know that this is going to be a decay. Therefore, since we're involving a percentage rate, guys, we're going to say y equals our a value times 1 minus r to the t power to write this. Okay, guys, well, what is the starting value of this car? Right off the bat.
10,000.
So what has to take the place of a? A always represents your starting value. What are you going to plug in for a, kids? $15,000. And then we're going to have 1 minus, okay, your percentage rate R must go in as a decimal. So what's 10% look like as a decimal when you move that decimal back to the left 2 places? How much? 0.1 or 0.10? All to the t. Well, guys, what is 1 minus 0.10? What is 1 minus 1/10?
0.9.
0.90. Okay? Now think about it, kids. This here is our function to model the problem right here. Take a look at that change factor there. What is the change factor? What value is the change factor when we get to that point?
10% negative.
So 10% decrease. This 0.90, is this between 0 and 1 or more than 1?
Between 0 and 1.
Which means if it's less than 1, this is going to show decay, right? So does my model make sense in terms of what's going on here? Absolutely. Okay. All right. It says find the approximate monthly percent decrease in value. Well, this is kind of an interesting question because it loses 10% every what, kids? Every year. So I'm going to write here this. Well, we lose 10% each year. Guys, how many months are in a year?
12.
So if they want to know how much you lose each month, what percent you lose each month, wouldn't I take that 10% a year and divide it by 12 months in a year? Yeah, so each month you lose 10% divided by 12 months. What is 10 divided by 12, kids? Is that 0.83 repeating?
Yep.
Or 0.83%. Okay? A little less than 1% each month you lose value on that. Okay? A little less than 1% each month. Okay? Now guys, I'm not even going to use the graph. I'm just going to estimate the value. I don't care about graphing. Where would you graph this, kids? Where? And you'd say, well, it's exponential decay, so it's going to look like this, isn't it? Right? So that's going to be the shape. I'm just worried about the shape. I'm not going to get excited about the graphs of these. Okay? So the question goes on to say, what's the value of the car in how many years, kids? What's the value of the car in 6 years? Well, doesn't T represent the number of years here, kids? So where are you going to throw 6 in at? Right there. Okay, so the value of the car after 6 years is, all right, have your calculators handy, you kids. I'm gonna run you through this again. Okay. You guys ready that I plug 6 in for T? So here's how I want you to handle this. The best way I think to do this is to do the exponential part first. So in your calculator, go 0.90 to what power? Go 0.90 to the 6th power. See what that number is. I don't know what that is. But once you've done 0.90 to the 6th power, what are you going to multiply that answer by?
15,000.
The 15,000 initial value. Okay, so let's all agree that we've got the right value. I'm going to go 0.9 to what power first, kids? Okay, now I want to take that times.
15,000.
So Gage's $15,000 hot rod, he's been driving around for 6 years now, is worth how much money?
7,000.
Still worth $7,000. Maybe in 6 years he's paid it off already. Okay? Maybe he's already paid that off in 6 years. So maybe he wants to get rid of it now. How much money is he going to get back? Or could get back?
Almost $8,000.
Almost $8,000. Okay? Is that a good investment? You drive it long enough, pay it off, and you get $8,000 back. Is that a good investment? Absolutely. Okay, so after 6 years, what was the value here, guys? Have you got it in your calculator? Mine's going to go away. So that, what was it, 7,000?
71.62.
Now, guys, I know that you've done a great job taking notes. Okay? And I'm going to keep preaching to you that if you're not sure about something, find an example in here to go off of. Okay? There's a lot of new stuff in this section, I think. I really think examples 4 and 5 today are crucial. If you can understand 4 and 5 or work to better understand them as you see some of the problems on the quick quiz today or any online I'm going to send out while I take the quick quiz, I strongly encourage you to take a look at those again if you're not sure about something, okay? So, that's it. I don't think I sent an online page out yesterday, did I? So let me stop this here.